Hi everyone, this starts our brand new unit, and specifically our first day of 5.1, which is titled 5.1 Trigonometric Identities. And all identity means, let's define it to start, is left side equals right side of an equation for all values of x. So for example, if I wrote x squared minus 9 divided by x minus 3, and I said that that equaled x plus 3, is this an identity? Let's see. Well, recalling my Algebra 2 knowledge, I can factor x squared minus 9 as x plus 3 times x minus 3, still divided by x minus 3. And again, does left side equal right side? We'll see. The x minus 3's cancel, leaving behind x plus 3 equals x plus 3. And that is true, which makes the original statement right here an identity, because the left side does equal the right side for all values of x. Let's start looking at our trig identities and first start talking about the reciprocal identities. So now taking a step back into trig versus Algebra 2. So sine of theta is the same as what? I'm hoping this keyword reciprocal is ringing a bell. Sine of theta is equal to 1 divided by cosecant of theta. In similar fashion, cosecant of theta is equal to 1 divided by sine of theta. So for any value of theta that you input, left side will equal right side. See if you can write cosine of theta on your own. What are we saying cosine of theta equals? If you wrote 1 divided by secant of theta, I agree. Secant of theta is 1 over cosine. What is tangent of theta equal to? 1 divided by cotangent of theta. And then, last but not least, cotangent is equal to 1 divided by tangent of theta. So these 6 are called our reciprocal identities. Space them out a little bit. Next, we have our quotient identities. Quotient meaning a ratio. Tangent, excuse me, if I think back to my unit circle, was always y divided by x. If I'm on the unit circle, y is my sine value, so sine, and x is cosine. So tangent of theta equals sine of theta divided by cosine of theta. Left side will equal right side no matter the value of theta you choose, which means cotangent of theta is, if tangent is y over x, cotangent is x over y, so cosine divided by sine. So we've talked about our reciprocal identities, our quotient identities, and next we are going to discuss our Pythagorean identities. To discuss this, please kind of visually cut your paper in half right now and leave the left side blank. Let's go back and just sketch a little unit circle over here so we have a reference to discuss so we can connect some prior knowledge. If I'm on the unit circle and I create a radius here, if I'm on the unit circle, that radius is 1. And I create an ordered pair here on the unit circle, I would go right x and up y to get the ordered pair x comma y. So just to visualize that. Again, from 0, 0, from the origin, I would go right x, up y. From our prior learning, though, if I'm on the unit circle, it's not just an xy ordered pair. That is actually cosine of theta, whatever that angle is. Cosine of theta, sine of theta. This is a right triangle. So using the variables I see here, I could write x squared plus y squared equals 1 squared. But knowing I'm on the unit circle, x here is cosine of theta. So I can write cosine of theta squared plus y, but now y is sine of theta squared, equals 1 squared is 1. So this is our first Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Notice I can write the square outside with parentheses. So if you're going to put the written squared term at the way end like this, you have to have this in parentheses. If you don't want to use parentheses, you can write sine squared of theta, or sine of theta squared this way. Now, what if I asked you to solve for a value here? I'm just pausing for a second to think of how I want to ask you my question. We can, from this identity, derive 2 more. So let's start. We're going to come back over here to our workspace. Sine squared of theta plus cosine squared of theta equals 1 is what we're starting with. Remember, I can do anything I want to this equation as long as I do it to all terms. So let's see what happens when we divide by sine squared of theta. Remember, I can do anything I want as long as I apply that mathematical operation to all terms. So if I divide each of these terms by sine squared of theta, the result will be the following. Anything divided by itself is 1, so sine squared of theta divided by sine squared of theta simplifies to 1. What is that? Well, coming back up to our quotient identities, check it out. Cosine divided by sine is cotangent. So cosine squared divided by sine squared is cotangent squared. And then from the notes you've taken so far, what is 1 divided by sine squared of theta? Take a look. And let's see if we agree. So looking at 1 divided by sine, come up here, and my attention comes to this guy right here. So if 1 divided by sine of theta is cosecant, 1 divided by sine squared will be cosecant squared. So there's our second identity. And that came from taking that first identity and dividing by sine squared. So let's write it over here. 1 plus cotangent squared of theta equals cosecant squared. Let's reset. Come back here to sine squared of theta plus cosine squared of theta equals 1. And can you guess what we are going to divide by next? Well, we explored what happens when we divide by sine squared of theta. Now let's see what happens when we divide by cosine squared of theta. Or cosine of theta squared. I would challenge you to press pause and see if you can actually write the result on your own. We're taking our notes in pencil, so if you need to adjust, that's perfectly fine. But press pause, see if you can do it using your notes. Alright, let's see if we match. So sine divided by cosine. In my brain, I'm thinking y divided by x, and I remember that that's tangent. So I know that this is going to be tangent of theta squared. Cosine squared theta divided by cosine squared theta is 1. And then 1 divided by cosine, I will either remember is secant, or I will study so that I know this without hesitation. So this equals secant squared. So our third and final Pythagorean identity is tangent squared of theta plus 1 equals secant squared. So right now we have 6, 7, 8, 9, 10, 11 identities in our toolbox. And we can actually get a couple more by analyzing how we can rewrite these 3. So let's just take a second and explore what happens when we start rewriting. The Pythagorean identities. So let's start with that first one. Sine squared plus cosine squared equals 1. Well, if I solve this for cosine, this is going to be cosine squared equals 1 minus sine squared. So literally, if I'm trying to isolate this term, I would subtract over sine squared of theta. So here's 1. If I was, I don't know if I like the arrow. I don't want to be confusing with my... Yeah. I don't know. No, I don't like the dot either. Alright, I'm just going to use an arrow. So I'm saying this list that I'm writing comes from this one, okay? If I'm trying to solve for sine, sine squared equals, well, to isolate sine squared, I would subtract over cosine. So 1 minus cosine squared of theta. Let's now take a look at our second one here. 1 plus cotangent squared. And once again, let's see how we can rearrange. Right now, it's a little messy. Let me rewrite it. 1 plus cotangent squared. It's cosecant So right now this equation equals cosecant. Cosecant squared is the isolated term. I can isolate 1. So 1 equals cosecant squared of theta minus cotangent squared. Or I could isolate cotangent. Cotangent squared theta equals cosecant squared minus 1. And now let's take a look at our last one here. Tangent squared plus 1 equals secant squared. Once again, I could start off by saying, well, what if I want tangent squared by itself? That's going to be secant squared minus 1. I could even say, well, what if I want, what does 1 equal? 1 equals secant squared minus tan squared. I could even take this one divide by negative 1 and arrive at a third one. Dividing this by negative 1, I would get negative tangent squared equals, so this would become negative, this would become positive, which is the same thing as saying 1 minus secant squared. So it kind of flips this order. So I'm just making a point that really the possibilities are somewhat, they're not literally endless, but somewhat endless in how we're able to rearrange. Because I just took those 3 identities up here and generated 1, 2, 3, 4, 5, 6, 7 more. So these would make great flashcards. I would absolutely recommend that we make flashcards of these 6 reciprocal identities, these 2 quotient identities, and these 3 Pythagorean identities. And over time, we will absolutely develop a comfort level with working with them. But for right now, flashcards would be great if we're in doubt. Let's get into some examples. So this is going to be simplifying examples. Number 1, simplify cotangent of x times sine of x. So to simplify it, we're looking to rewrite in a way that something can cancel. So sine of x, I technically could rewrite that as 1 over cosecant. That's not really going to get me anywhere. But how can I rewrite cotangent? Take a second and look. What does cotangent equal? Well, I go up here, remind myself that cotangent is 1 over tangent, not so helpful. But how about cotangent is cosine over sine? That could be useful to pull out of the toolbox. So let's see. If I write cotangent as cosine of x divided by sine of x, and that's still being multiplied by sine of x, which is technically divided by 1. So if it helps you to write divided by 1, do so. Notice what happens. Sine of x here in the numerator cancels out with sine of x in the denominator, equals cosine of x. And that's as simplified as we get. So this is our first example of how we're going to use our identity knowledge to simplify. Number 2. So from this point forward, the directions are always going to be simplify, but I'm not going to continue to rewrite that word. So number 2 is cosine of x times tangent of x. Once again, cosine here, I'm going to leave alone because when I see tangent, my first thought is cosine of x is going to stay what it is. but I can rewrite tangent how? Tangent is sine of x divided by cosine of x. Rewritten as such, I now see that cosines will cancel, leaving behind sine of x, and there's nothing else I can do from there. It's as simplified as it gets. Number 3. Cotangent of x divided by cosecant of x. Interesting. Now realize that simplifying in some ways is an art form, right? You have this giant menu of options and we need to choose the one that's strategically good for us. But maybe I choose one it doesn't work out. That's okay. You're writing in pencil. So for cotangent, what do we want to try for cotangent? Well, it worked before to start seeing it first as cosine of x divided by sine of x. So I'm going to start there. That is all divided by, and notice how I make this division bar much, much bigger, cosecant of x. So if I'm trying to be strategic, this is going to be good for me to remember that cosecant is connected to sine, and my question would be how? Well, cosecant of x I can rewrite as 1 divided by sine of x. When we are dividing fractions, we keep the first, so that's going to stay cosine of x divided by sine of x. Change division to multiplication and flip the denominator. So this will be now sine of x divided by 1. What can happen now? Well, now my sine of x's cancel, and the result is cosine of x. Number 4. Secant squared of x multiplied by 1 minus sine squared. My first thought when I see secant squared is that I can write that as 1 divided by cosine squared. I almost wrote theta, but we're dealing with x now. So 1 divided by cosine squared x. Now 1 minus sine squared of x might not jump out at us yet, but with familiarity and practice, as soon as I see that, I will be thinking of this guy right here. That 1 minus sine squared equals cosine squared. It's one of my Pythagorean identity rewrites. And, by the way, if you forgot that, you can always come back to cosine squared plus sine squared equals 1. So if I remember that, and I'm trying to get to something that looks like this, well, 1 is already over here. If I subtract sine squared from both sides, I get cosine squared equals 1 minus sine squared. So if we remember the parent ones, so to speak, when I say parent ones, I'm talking about these original 3 Pythagorean identities. It's very powerful because from these 3, you can work towards what you need. Don't feel like you need to memorize all these if we know how to obtain them as we need them. So using that identity, I now know I can rewrite 1 minus sine squared as cosine squared. If it helps, make sure it's divided by 1 because it's in the numerator. Cosine squared is in the numerator. Check it out. What's going to happen cosine squared theta cancels with cosine squared theta equals 1. Number 5, sine of x times cosecant of theta minus, and that should be x, sorry, don't mean to mix it up, cosecant of x minus sine of x. So sine of x, nothing really I can do there. Now let's take a look at what we have on the inside. Now, as nice as it would be to come up here and start looking at some of our Pythagorean properties, notice these are all squared trig functions. Squared, 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 squares everywhere. Nothing squared here in number 5. So I can't use any of my Pythagorean identities, but I can use my reciprocal identities. So let's see what happens if I leave sine of x alone. How can I rewrite cosecant? Well, cosecant is the same as 1 divided by sine of x. And for the moment, I will leave sine of x by itself, or not by itself, alone. That's interesting. And then let's see what happens if I distribute sine of x. This becomes sine of x divided by sine of x minus sine squared. Well, sine of x divided by sine of x is 1. And now I'm back into squared values. So I need to consider, is this possibly connected to a Pythagorean identity? And on the screen here, it just so happens we have that one we were manipulating before. Notice cosine squared of theta equals 1 minus sine squared. 1 minus sine squared equals cosine squared. That's as far as we can take it. Number 6. Tangent squared divided by secant squared. Tangent squared divided by secant squared. As soon as I see tangent, my first go-to thought is sine squared divided by cosine squared. So I'm going to start there. Maybe it's helpful, maybe it's not. We'll have to see. All divided by, how can I rewrite secant? Secant is the same as 1 over cosine squared. Keep, change, flip. Go from there. Press pause, see how it goes. So I keep the first fraction, change to multiplication, flip the second fraction, and check it out. Cosine squareds cancel, leaving behind sine squared. We will be working out of a worksheet that's page 346 on the worksheet that you will get tomorrow. So I'm going to put page 346 as a reference for the odd examples we're about to work on. So this one is going to be page 346, number 51. And that example says cotangent squared minus cotangent squared of x times cosine squared. So if you want to shift this down and give it a title, if you have space to squeeze in a little title here, these are going to be our factoring examples. My biggest recommendation would be off to the side, if I create a little brain bubble here. If I let cosine squared, or excuse me, cotangent of x squared just be x squared. This, I could mentally see it as x squared minus x squared, right? You have another cotangent squared. And then cosine squared x, I'm just going to let that be a different variable. So if I had written that in Algebra 2 and I asked you to factor that, what would you tell me you could do? And my hope is that everybody is thinking or saying right now, GCF, and I would agree with you. Because if I factored out an x squared, that will leave behind 1 minus y squared. So let's see how that's going to apply to ours over here. Our GCF right now is cotangent squared. Factoring out cotangent squared, we'll leave behind 1 minus cosine squared. One minus cosine squared rings a bell. And maybe I'm going to say, I don't want to look at my notes, I want to figure it out. So I remember cosine squared theta plus sine squared theta equals 1. If I subtract cosine theta minus cosine squared, I get sine squared theta equals 1 minus cosine squared. And notice, 1 minus cosine squared. So, using that knowledge, I can now say cotangent of x squared multiplied by sine squared. But wait, there's more, because how can I rewrite cotangent? Cotangent is the same as cosine squared divided by sine squared. What do you see can cancel? My sine squareds cancel, leaving behind cosine squared. Number 53 is cosine squared of x minus 4 divided by cosine of x minus 2. Once again, let's take a little step over into algebra land. I'm going to let this cosine squared term just be x squared minus 4. And then plain cosine would be x, and then minus 2. So if I asked you, I'm just going to make it match. How you would factor this, I'm hoping we're saying, ooh, x squared minus 4, difference of squares, divided by x minus 2. Those x minus 2's will cancel, leaving behind x plus 2 as an answer. So let's see how this applies to our example over here. We can factor this to be cosine of x plus 2, cosine of x minus 2, and it's still all being divided by cosine of x minus 2. Check out what cancels. Cosine of x minus 2 cancels with cosine of x minus 2, leaving behind cosine of x plus 2. 55. It's our second to last example. Tangent of x to the fourth power plus 2 tangent of x squared plus 1. Once again, let's step over back into Algebra 2 land. I choose to write in my brain and on paper that this is the same as x to the fourth plus 2x squared plus 1. And my hope is that we recall this is quadratic-like. Because it's not a quadratic, right? It's a fourth power. But I can factor this as x squared plus 1. X squared plus 1. Similar to if this had been x squared plus 2x plus 1. Remember, factors of c that add to b would be x plus 1 and then also x plus 1. So that's why we call it quadratic-like. It factors similar to how this would factor if it was a quadratic, but instead it's a power of 4. So applying that knowledge to our example over here, this can factor tangent squared plus 1, tangent squared of x, or tangent of x squared plus 1. Let's go look at our menu of Pythagorean identities. We're looking for one that has tangent of x squared and 1 in it. See if you can find it first. I've got that guy. So let's bring that down. So tangent squared plus 1 equals secant squared. Tangent squared plus 1 equals secant squared. That's exactly what I need. Check it out. Tangent squared plus 1, tangent squared plus 1. So this becomes secant squared of x times secant squared of x, which becomes secant to the fourth power. And I am done. Last example. Which says cosecant cubed, third power, minus cosecant squared minus cosecant plus 1. Stepping into algebra world, let's see what this will become. If we mentally and physically rewrite it in terms of x. So this would be x cubed minus x squared minus x plus 1. Remember, when we have 4 terms, we always consider, can we factor by grouping? So if I consider factoring this by grouping, out of this first group, I can factor out x squared. I'm going to need a slightly bigger bubble. Leaving behind x minus 1. Factoring out a negative 1 from the second grouping leaves behind x minus 1. And then notice the common term, x minus 1. So to complete the factor by grouping, if I literally factor out x minus 1, it would leave behind x squared minus 1. But wait, there's more, because x squared minus 1 is the difference of squares. So I could technically keep going and say x plus 1, x minus 1, x minus 1. So my final answer here would be x plus 1, x minus 1 all squared. So let's apply that idea of factor by grouping to this example and see what happens. I can factor out cosecant squared, which leaves behind cosecant minus 1. And if I factor out a negative 1, I get cosecant minus 1, which is awesome because now I have that common group. Factoring out that common group, I have cosecant squared of x. Don't leave the x behind. And don't spell cosecant wrong, like me. Minus 1, cosecant squared minus 1, and then cosecant of x minus 1. Let's see. What are our thoughts? Well, this guy I'm going to leave alone because I don't see a square term. But over here, let me go see if I have a Pythagorean identity that we can use on it. So I'm not going to move my screen because I don't want this to change. But can you look in your notes and see if you can find a Pythagorean identity that we can use on that first factor? My hope is that your attention is drawn to the identity that says 1 plus, now I will move the screen because I really want to make sure we're looking at the same thing. This guy right here. That 1 plus, and I want that to be green. 1 plus cotangent squared is cosecant squared. So let's write that down, just for the sake of our notes. 1 plus cotangent squared equals secant squared. Excuse me, cosecant. So if I subtract 1 from both sides, notice this becomes cotangent squared equals cosecant squared minus 1. Check it out. Cosecant squared minus 1, cosecant squared minus 1 matches. So I can rewrite this first factor as cotangent squared and this second factor will stay. Maybe if this minus 1 wasn't there, I could consider something else, but it's not squared. I'm done. So that ends our notes for today. Definitely an intense step back into algebra, specifically for the factoring examples. So as I scroll up, look at what's in blue. What's in blue is the Algebra 2 factoring knowledge that was key to each of these examples. So we're definitely going to be bringing that back. If you have a couple extra minutes, I'd recommend maybe taking a blank piece of paper and rewriting one of the notes examples and giving it a try and seeing if you can get there, right? So tomorrow will be full of, first, answering questions on the notes, and second, practice, practice, and more practice. Have a great night, guys, and please, as always, any questions, send me a reminder. Have a good night.